Hello students, so we are going to see in this session the continuity topic. In the previous session we have done the recapitulation of limits and what we have learnt in first PUC. We have completed entire the limits topic which we have studied earlier, and we made some foundation for this continuity. Okay. So now we are going to see the topic continuity. So continuity of a function means suppose if we take a function fx is equal to x, a function fx is equal to x I have taken, fx is equal to x. You know its graph, y is equal to x it is, y is equal to x, right. So y is equal to x graph, it comes like this. It's a principal diagonal, okay, of the coordinate axis. See that all the points 1 1, 2 2, 3 3, 4 4. In the same way here is 0 0, right. Here minus 1 minus 1, minus 2 minus 2, like this. All the points x and y values will be equal in this, right. So the graph of this function y is equal to x is a straight line, will get like this, right. So when you observe its graph in a single stroke, if you are able to write, if you are able to draw it or not, yes, in a single stroke without lifting the pen on the paper or otherwise without lifting the chalk on this board, in a single stroke I can draw this graph. Then I can say that this function is continuous. Okay. One more example I take it. Fx is equal to x square. If you are able to draw the graph in a single stroke, okay, if you are able to draw the graph in a single stroke, then we can say that the function is continuous. See that in a single stroke, means without lifting the chalk, I can complete the graph. Okay. That means we can say that the function is continuous. Okay. It is a geometrical way, we can say, in a geometrical way. That means by just, if you are able to draw the graph in a single stroke without lifting the chalk on the board or otherwise without lifting the pen on the paper, if you are able to draw it in a single stroke, then we can say that the function is continuous. Okay. But whether it is possible every time to draw the graph and to say that it is continuity or continuous function, it's difficult because we know only few graphs, some standard graphs only we know it, but we don't know all the entire graphs of the functions. That's why we have to use with the concept of limit, we are going to check whether the function is continuous or not. Okay. So with the help of the concepts of limits, we are going to see the development in this topic. So we'll see what is the definition of continuity of a function at a point x equal to a. Continuity of a function at a point x equal to a. Suppose f is a real valued function, and x equal to a be a point in the be a point in the domain of the fx, in the domain of fx, if limit extends to a, fx is equal to f of a happens. If limit extends to a, fx is equal to f of a happens, then we say that fx is continuous at x equal to a. Okay, f is a real valued function and x equal to a be a point in the domain of fx, and if limit extends to a, fx is equal to f of a, then we say that fx is continuous at x equal to a whenever this happens. Elaborately, if you want to say that the left hand limit and right hand limit and the function value, all the three must be existing and equal. Okay? So, left hand limit, right hand limit both has to exist and they must be equal, and the limiting value must be equal to the functional value. Then we say that the function is continuous at x equal to a. Okay? So, limiting value, you know how to find it out. In the previous session I have clearly explained how to find the limiting value of the function. And functional value, that means right away you substitute that point in the function, you will get functional value. When these two are equal, then we say that the function is continuous. Okay. Now, we will see some problems. The function is continuous at a particular point or not. And remember that the important thing is x equal to a is a point in the domain of fx. That is very, very important. X equal to a is a point in the domain of fx. That means continuity we will discuss only within the domain. Suppose I am having a function like this here, fx is equal to x square minus 9 by x minus 3 when x not equal to 3, and I define the function value at x equal to 3 is 6 like this. Okay. So, what about its continuity at x equal to 3? At x equal to 3 we need to discuss its continuity. In the previous session I have explained clearly about this function and its limiting value when x is equal to 3, right. So, what we got in the previous session, this limiting value, limit extends to 3 fx, we got 6. I have clearly explained that how we got 6. And here the function value they have given f of 3 is equal to 6. It is defined like that. When x equal to 3, the function value is 6 they have given. So, now when you observe it, the limiting value is same as the functional value now is equal to f of 3. So, I can say that the function is continuous at x equal to 3 now, right. So, that means there is a hole previous when x is not equal to 3, we have drawn its graph. Okay. Just recall it, y is equal to x plus 3 when x not equal to 3, right. This is the graph we have, right. In previous session we saw this, and now when x equal to 3, the value is 6. This gap is filled now. This gap, whatever the hole is present, that is filled now. So, that means I can draw this graph in a single stroke now. So, this function is continuous at x equal to 3. It is just a straight line. In a single stroke I can draw it, right. So, this function is continuous at x equal to 3 now. Next, we take a function fx is equal to 1 if x less than or equal to 0, if x less than or equal to 0, 2 if x is more than 0. Okay. So, simple examples I am taking, try to understand the continuity at a point. Now, we will discuss its continuity at x equal to 0. Okay. At x equal to 0, what happens to this function? What about its continuity? Okay. Try to understand first where the function is splitting, where the function is splitting. When x is less than 0 and equal to 0, they given the function value is 1. When x is more than 0, they have given the function value is 2 here, right. So, now when I take its graph, it is not difficult one, we draw the graphs. By graphs we can understand more clear. Now, if I draw its graph, okay, here x less than or equal to 0 for all negative values and equal to 0. At 0 they have given it is 1 only, right. When x equal to 0, function value they are given 1, and for all x negative values they have given it is 1 only. That means if it is minus 1, it is 1 only. If it is minus 2, then also it is 1. If it is minus 3, then also it is 1. So, when you join all these points, right, we will get like this. This is the graph. When it is a minus 1, also plus 1 only. When it is a minus 2, also plus 1 only. When it is minus 3, then also it is plus 1 only, right. So, like this we get. For all x greater than 0, for all x greater than 0, they given it is 2. That means more than 0. That means it won't touch here at 0. So, you must understand this is a whole. Whole means it is not included in the graph, but thick dot is included in the graph. We have to understand these are the notations. Like this we get. Okay, this is 2. When you take 1, the value is 2. When you take 2, also it is 2. When you take 3, then also it is 3, like this, right. So, we are having these are the y value is fixed there 2, and here it is a minus 1 1, minus 2 1, minus 3 1, like this. Now, when you observe it, the graph clearly, when you are coming close to 0 from right side, limit extends to 0 plus. What about its limit? It is very easy. Now, coming close to 0 from right side, the value, the y value is coming close to 2, it is coming close to 2. And when you are coming, when x is coming close to 0, when x is coming close to 0 from left hand side, at the time it is very clear from the graph that it is coming close to 1 it is. That means limit extends to 0 from left, fx you are getting 1. Limit itself is not existing here, right. The left hand limit is not same as right hand limit. That means limit extends to 0 plus fx is not same as limit extends to 0 minus fx. That means limit extends to 0, fx does not exist. It does not exist. Limit extends to 0, fx does not exist. Okay. So, then how we can go for continuity at x equal to 0 now? We know f of 0 value, right. What is f of 0 value here? Equal to 0, they have given 1. F of 0 we got it 1, f of 0 is 1, but limit is not existing. Okay. So, limiting value does not exist, function value we have, but when we say it is continuous, when the limiting value is equal to the function value. So that's why what I can conclude now, this function is not continuous at x equal to 0. It is not continuous at x equal to 0, right? Are you clear with this example? One more example we will see. Fx is equal to 1 if x not equal to 0, if x not equal to 0, and it is 2 if x equal to 0. Okay. Another example I have taken like this. Fx equal to 1 if x not equal to 0, fx is 2 if x equal to 0. We will discuss this continuity at x equal to 0 now. Here x not equal to 0, that means what all the possibilities are there? X not equal to 0 means either x is less than 0 or otherwise x is more than 0. That means for all x negative values it is 1, for all x positive values it is 1 only. But when x is equal to 0 it is 2 they given. That means it is a simple graph it is, we can write except 0. For except 0 it is always 1, right? That means it is a straight line it will be. Like this, right? Because they mention clearly except 0, the function value is always 1. Okay, it is a parallel line to the x axis. It's y is equal to 1. Now, when x is 0, they have given it is 2. Okay. When x is 0, they have given the value 2. When x is non-zero, function value is 1 all the time. Now, we will discuss its limit at 0. Now, when you observe it, when you are coming close to 0 from right side, the function value is what? It is coming close to 1. When x is coming close to 0 from left hand side, then also the y value is coming close to 1. That means what I can write, limit extends to 0 plus fx is 1 and limit extends to 0 minus fx is also 1. So, limit extends to 0, fx is 1 it is. That means we got its limiting value is 1. But what about its functional value? What about f of 0? They clearly mention f of 0 is 2. F of 0 value is 2. You got limiting value and you got function value, but they are not equal. Limiting value is there, function value is there, but they are not equal now. See that limit extends to 0, fx is not equal to f of 0. So, we say that the function is not continuous or discontinuous at x equal to 0. The function fx is discontinuous at x equal to 0. It is not continuous. Though limiting value existed, function value is there, but they both were not equal. That is why the function is not continuous at x equal to 0. In the previous example, limit itself is not existed in the previous example. Okay. So, we will check the continuity of the function. We will write one more question. Check the continuity. Check the continuity of the function fx is equal to 5x minus 3 at x equal to 5. Check the continuity of the function fx is equal to 5x minus 3 at x equal to 5. So, from here onwards we will see the actual problems by using limits concept only. We are not going to draw the graphs. Okay. So, f(x) is equal to given function. f(x) is equal to 5x minus 3. It is a linear polynomial. Okay. Linear polynomial, it is defined throughout the real number system, right. I have already mentioned that in the previous session. The polynomial function is defined throughout the real number system. Here f(x) is clearly defined at 5. Okay. f(x) is defined at x equal to 5, and f of 5 is what? What is f of 5? 5 into 5 minus 3, 25 minus 3, we get 22, right. That means the functional value is 22, and then we will find out the limiting value. Limit extends to 5 f(x). Here one point, very important point you have to understand, that the function, whether it is splitting at 5 or not, that is very important. If it is splitting at 5, then you have to go for left hand limit and right hand limit. But here at x equal to 5, it is not splitting. So that's a very, very important point you have to remember. Whenever the function is splitting where you are working, then there may be a need of left hand and right hand limits. Be careful. So limit extends to 5, f(x) is equal to limit extends to 5, 5x minus 3. I am not working here left hand and right hand limits. At just single stroke I am writing limit extends to 5, because the function is not splitting at x equal to 5. That means less than 5 one function, more than 5 one function is not there. It is for entire real number system, this is the function they are given. Okay. So limit extends to 5, 5x minus 3, what we can, because it is a linear polynomial, I have already told you the point that you can directly substitute this, right. We have discussed in the previous session, limit extends to a, if it is a polynomial p of x, straight away the value will be p of a. So now I am substituting here, what happens? 5 into 5 minus 3, 25 minus 3, 22. So limiting value is also 22. When x is coming close to 5, 5x come close to 25, 25 minus 3, 22. So therefore, limit extends to 5, f(x) is same as f of 5. So we say that the function is continuous. The function is continuous at x equal to 5 it is. The function is continuous at x equal to 5. Are you clear? So first we have to see whether it is defined at that point or not. Next, your next thing is you need to find out the functional value. Next you need to find out its limiting value and see that the limiting value is same as functional value or not. If they both are same, then we conclude that it is continuous at x equal to the given point. Okay. So right, we will see one more question. Check the continuity of the function f(x) is equal to mod x, f(x) equal to mod x at x equal to 0. They mention at some particular point at x equal to 0. So, you know, f(x) is equal to mod x. By the definition of mod x, what I can write? It is minus x if x is less than or equal to 0, plus x if x is greater than 0. This is the definition of mod x, right? This is the definition of mod x. I am not using graphs. I told you, no, though I know the graphs, I am not using now. I am working with the help of limits concept. Okay. Minus x if x less than or equal to 0, and plus x if x is more than 0. Now, it is very clear the function is splitting. The function is splitting at x equal to 0. Okay. So then I need to work it out. When you are working at 0, you have to go for left hand and right hand limits compulsory. Left hand limit, right hand limit, you have to work. So, f of 0 first. What is f of 0? This is equal to 0, either you keep here or here, no problem, okay, in mod definition. So, f of 0 will be, what do you get? Mod 0, straight away I kept in this, so I got 0 it is. This is a functional value. And limiting value. So, when you go for limiting value, I need to work it out compulsory left hand limit and right hand limit. We have to habituate this, because wherever the function is splitting, when you are working at that point, you have to do compulsory left hand and right hand limits. So, limit extends to 0 minus fx. So, limit extends to 0, 0 minus, the meaning is what? You are approaching the 0 from left hand side. That means you are coming close to 0. You are coming close to 0 from left hand side. The meaning is x value will be less than 0. You are coming close to 0 from left hand side. That means when x is coming close to 0 from left hand side, the x is less than 0. When x is less than 0, what is the function? Minus x. So, then you can substitute now minus 0, 0. See, in the place of this, I not wrote again 0 minus. Why I not wrote? Why I not wrote? That also you try to understand. The 0 minus work is what? To know what function you are to write in the next step. Okay? That is the only job of this minus. Okay? So, what it indicates? Your x is coming close to 0 from left hand side. Then what function you need to take, that it will decide, right? After that I not wrote 0 minus again. Its work is over, its job is over there. That is why I wrote minus x right away, this function here based on this. So, minus x, so minus 0, 0 I got it. And then right hand limit also. Limit extends to 0 plus fx. Limit extends to 0. 0 plus, that means you are approaching the 0 from right hand side. That means the values will be more than 0, right? When you are coming close to 0 from right hand side, the x values will be more than 0. When x is more than 0, what function I have to take it? X I have to take it. So, it will be 0. It is a simple thing only, but try to understand what is the need of left hand and right hand limits. Okay. So, left hand limit value 0, right hand limit value 0. So, I can conclude that now limit extends to 0, fx is 0 and which is equal to f of 0, which is equal to f of 0. So, that means the limiting value is same as functional value. Therefore, we say that fx is continuous at x equal to 0, right. So, whenever you are working for continuity at a point, first see that whether it is defined at that point or not first, right. This function is clearly defined at x equals 0. That also you mentioned that point, that is a very important thing. F is defined at x equals 0, because you are working at that point. F is defined at x equals 0 and f of 0 is 0. In the next you have to go for limiting value. Whether you are working left hand right hand limits or just right away limit extends to 0 fx is depend upon the function. Okay. We will work it out still more problems, so that we will understand more about this continuity. Okay. Right, next function we check the continuity of the function fx is equal to x cube plus 3 x cube plus 3 when x not equal to 0. Okay. 1 if x equal to 0. Okay. Check the continuity of the function fx x cube plus 3 if x not equal to 0, 1 if x equal to 0, at x equal to 0. Okay? At x equal to 0. So, fx is equal to x cube plus 3 if x not equal to 0, 1 if x equal to 0. X not equal to 0 meaning is what? X not equal to 0 means either x is less than 0 or x is more than 0. Both possibilities are there. Okay? Either x is less than 0 or x is more than 0, the function is x cube plus 3. Okay? 1 if x equal to 0. So, this is a polynomial function it is defined everywhere, right? And at 0 they have given 1, that means what is the domain of this function? The domain of this function is a real number system, right? Clearly, f is defined throughout the real number system, Okay? So, that means what is the domain of this function? Domain of fx is R. Domain of this function is R. Now, at x equal to 0 we are working. At x equal to 0 we are working. So, what is f of 0? They are mentioned clearly, f of 0 is 1. Now, you tell me whether we need left hand limit and right hand limits to work at 0. It is not required, because when x is less than 0, this is the function. When x is more than 0 also, this is the function. Whether you are approaching from right side or left side, okay, approaching to 0 from right side, 0 plus, x is coming close to 0 from left side, here x is less than 0, here x is more than 0. When you are working for this, x is more than 0, when you are working for x is less than 0, both the time the function is the same thing. So, in this case, we no need to work it out, left hand and right hand limits. Straight away, you work it out, limit x tends to 0, fx is equal to limit x tends to 0. See, I not wrote 0 plus or 0 minus here. Approaching to 0, that means either from left or right, whatever maybe it is. So, the function is what now? X cube plus 3. So, 0 cube plus 3. So, what I am getting? 3. Limiting value, I am getting 3. Okay? This is a main key point, okay, in continuity, whether you need to work it out left hand and right hand limits or just write away the limit. You study the function properly, then you can work it out the limit very easily. Okay, is equal to 3. So, what we got now? Limit value is 3 and function value is 1. Right? So, both were existed, but they are not equal. So, limit x tends to 0, fx is not equal to f of 0. So, what we conclude now? Therefore, fx is not continuous. Therefore, fx is not continuous at x equal to 0. Is not continuous at x equal to 0. Clear? So, this is working at some point. Continuity at a point we have discussed. When we say a function is continuous at x equal to 0, f is a real valued function and x equal to a is a point in the domain of the function, and limit x tends to a, fx is equal to f of a happens, then we say that the function is continuous at x equal to a. So, and we discuss some problems based on continuity at a point. Now, we will discuss continuity in the interval. Continuity of a function in an interval. Continuity of a function in interval, open interval AB. Suppose how we define, we see this. Continuity of a function in an interval, open interval AB. So, it is a very simple thing. The function fx is continuous at each and every point between A and B. Between A and B. Then we say that the function is continuous in open interval AB. That is it. If the function fx is continuous, the function fx is continuous at each and every point, at each and every point between A and B, then we say that the function is continuous in open interval AB. It is very simple. Whenever a function is continuous at each and every point between A and B, at each and every point between A and B, if it is continuous, then we say that the function is continuous in open interval AB. Okay. Next thing, continuity of a function in an interval, closed interval AB. In an interval, closed interval AB. Okay. If a function fx is defined in closed interval AB, it is a very important, always defined in closed interval AB, and first point, okay, first point, f is continuous at each and every point, between A and B. Second point, limit extends to A plus fx is equal to f of A. That means at point x equal to A. Okay. And third thing, limit extends to B minus fx is equal to f of B. Okay. Here you are working in this interval, closed interval AB. So that means the left hand limit at B is same as f of B, and right hand limit at A is equal to f of A, and f is continuous at each and every point between A and B. Then we say that, the function fx is continuous, and fx is continuous in closed interval AB. Are clear? Open interval AB and closed interval AB. So, continuity of a function in an interval, open interval AB. If a function fx is continuous at each and every point between A and B, then we say that the function is continuous in open interval AB, provided fx is defined in open interval AB. That is very important. Defined is the point, very important. Okay. So, I will mention here itself. Suppose fx is defined in open interval AB. This point we should not miss. Okay. Fx is defined in open interval AB. If a function fx is the same function, we continue. Suppose fx is defined in open interval AB and fx is continuous at each and every point between A and B, then we say that the function is continuous in open interval AB. And continuity of a function in interval closed interval AB, if a function fx is defined in closed interval AB and f is continuous at each and every point between a and b, and limit extends to a plus fx is f of a, limit extends to b minus fx is f of b, then we say that the function fx is continuous in closed interval AB. Here we can call this is a right continuous. In higher classes you study, this is called right continuity, and this is a left continuity at B. It's a right continuity at A. Okay, you don't confuse with that why you are considering this, because here you have to work within these limits only, closed interval AB only you have to work it. Okay, so for that I can tell one example for this. Suppose you are having suppose if you take a function, one good example I will explain it for this sake. Fx is equal to square root of 4 minus x square. One function I take it. Fx is equal to square root of 4 minus x square. What is its domain? What is its domain? Domain means for what values of x the function is defined. So if I take 4 minus x square greater than or equal to 0, then only this function is defined, right? F is defined when it is, f is defined when 4 minus x square is greater than or equal to 0. When we simplify, what happens? X square is less than or equal to 4, it should be. Then mod x is less than or equal to 2 when you take the square root. Then x is lie between minus 2 and 2. That means, what is the domain of this function now? Domain of fx is closed interval minus 2 to plus 2 it is. Domain of this function fx is closed interval minus 2 to plus 2. Whether this function is continuous in this interval or not, if they ask, okay, you can work it out very easily between minus 2 and 2, first point, first thing, by considering one of the point, you can work it out this one. Here, I want to explain this one mainly. Here, a plus and b minus. See, this is the domain minus 2 to plus 2. Okay. This is the domain of this function. Now, if you want to approach minus 2, you can approach only from right side. You cannot approach from this side. It won't allow. Why? Because it is not within the domain of the function. That's a very important point you have to observe it. Don't worry about minus 2 left hand side, what happens. The left hand limit at x equal to minus 2, what happens? You don't bother about it, leave it. Just work on only from right side of minus 2. And you have to work limiting value at 2 means only the left hand limit you have to work. You cannot work the right hand limit. Why? Because within the domain you have to work it. That's a very important thing. Within the domain where it is defined. Okay. It's just like if you apply some example, general example if we apply. Suppose this is your house. Okay. Suppose this is your house it is. Okay. Then neighboring houses are there. If you want to enter your house, you won't go to others' house and you won't jump from the wall, right? So if you do like that, they will call you as a thief, right? So you have to enter your house only through the gate which you are having, okay, right? And from this side you can't come, and from this side you can't come. That's why within the domain you have to work it out, right? Are you clear? So within the domain only you have to work always, right? That means limit extends to minus 2 plus you will work here. And what else you will work? Limit extends to 2 minus fx. Here it is going to be, okay, continuous at minus 2 and plus 2 also, this function. Okay, when you keep minus 2 plus and 2 minus, in both the cases this is continuous. You just substitute minus 2, what happens? You will get 0. Function value also, f of minus 2 also you will get 0 only. And 2 minus, in that case also you will get 0, f of 2 also 0 you will get. Okay, just I have given an example for you. Okay, right. And continuity in an interval we saw, open interval AB, close interval AB, and also one more last definition we are having, continuous function. Continuous function. What do you mean by continuous function? Or simply continuous? Continuous function. The definition of this is simple point, what we can say in simple manner is continuous function means a function if it is continuous in its entire domain. If the function is continuous in entire domain, then we say that the function is continuous. That means what is the meaning of that? If fx is continuous, if fx is continuous at each and every point, present in its domain. Okay? If fx is continuous at each and every point present in its domain, then we say fx is continuous. Right? If it is continuous at each and every point present in its domain, then we say fx is continuous. That's it. Continuity at a point, continuity in open interval AB, continuity in closed interval AB, continuous function. Continuous function means if f is continuous at each and every point present in its domain, then we say f is continuous. Now, we will see few problems based on this. Check the points. Where the constant function fx is equal to k, fx equal to k is continuous. Okay, this is the question. Check the points where the constant function fx is equal to k is continuous. Now, we know fx equal to k is defined everywhere. That means in the entire real number system it is defined, it is a constant function, right, given fx is equal to k. First of all, what is its domain? F is defined on R. In the entire real number system it is defined, f is defined on R. So that means domain of f is what? R. Now, is it mentioned at a particular point you have to work? No. Just you have to work it out at some point. Now what I do is, let C belongs to R be any point I take it. At some general point I am working now. Let C belongs to R be any point. Okay. Then f of C is what? Is k. Whatever it is, you substitute any value. F of C is k. Function value, you got it, k. And then limiting value. So the question immediately you should get whether I need to work it out left hand limit and right hand limit or not. Okay, not required because the function is not splitting. At any point it is not splitting. So limit extends to C, fx is equal to limit extends to C, k. K is a constant here. Okay, there is no variable to change also. So limit of a constant is constant k, you got it. Therefore, limit extends to C, fx is equal to k is equal to f of c. What do you mean by that? The limiting value of the function and the functional value at x equal to c is equal, right? Limiting value and function value at x equal to c, they both were equal. Then what we can conclude now? It is true for all the real numbers, right? Comma, it is true for all c belongs to R. For all c belongs to R. That means we proved for all the real numbers. Indirectly what we are saying here, we proved for all the real numbers. That means this function is continuous in entire real number system. So, fx is continuous at each and every point in the real number system, Hence, what we can write? Hence, f is continuous. There is no point of discontinuity in this. There is no point of discontinuity because they mentioned check the points where the constant function is continuous. It is continuous throughout the real number system. So, I can conclude that hence f is continuous because it is continuous in the domain. It is continuous at each and every point present in the domain. That is why we say that f is continuous. And next we take one more function. So, here also they are asking check the points where the identity function, identity function fx equal to x is continuous. Same. Here also they not mention at a particular point you work. That means you have to work in its domain. So, given fx equal to x, the identity function, given fx is equal to x, clearly f is defined on R. So, domain of f is R and you take any point present in the real number system, let c belongs to R be any point. At some general point you are working. So, f of c become what now? C. F of c become c now. So, limit extends to c, f of x will be extends to c here, the function is x here. So, you will get c. So, limit extends to c, f x is equal to c is equal to f of c you are getting. That means it is true for all c belongs to R. That means the limiting value is same as the functional value at x equal to c. It is true for all c belongs to R. So, f x is continuous at each and every point present in the real number system. Hence, f is continuous. Right? Just small modifications are done, that is it. Okay? This is another problem. f x equal to x is continuous. Identity function, okay, is continuous function it is. There is no point of discontinuity for this. Next, one more problem we take. Check the points where the modulus function fx is equal to mod x is continuous. Okay. So, given fx is equal to mod x, you all know its definition, mod x definition, minus x if x is less than or equal to 0, x if x is more than 0. This is the definition of this function. You observe it, it is defined throughout the real number system, but one point you observe, it is splitting at 0. It is splitting at 0. That means less than 0, one function, minus x, and more than 0, the function is given as x. Right? So, now it is splitting at 0, you have to understand. So, this one we can work it out in totally 3 cases because they are not mentioned particularly you work at x equals 0, something like that they are not mentioned. You have to work it out throughout real number system. Clearly, fx is defined define at each and every point, at each and every point in R. Okay. So fx is defined at each and every point present in R. Now, so what is the domain of this function? Domain of this function fx is R only. Now we will work it out. This is in 3 cases, right? It means less than 0, 1 case, equal to 0, 1 case, and more than 0, 1 case. Case 1. Because the function is splitting there, right? So 3 divisions we can do it. Case 1. Let C less than 0 be any real number. Be any real number. Be any real number. Then f of c is what? According to the definition, it will be minus c. F of c is minus c. Then we will work it out. Limit extends to c fx. You don't need to work it out left hand and right hand limits here, because you are working for less than 0 only. For less than 0, you are having only one function, whatever maybe it is, minus x. So limit extends to c minus x. So you are getting minus c. Therefore, limit extends to c fx is equal to minus c, which is equal to f of c, right? So limiting value and function value are equal. It is true for all c less than 0. That means what I can conclude now, fx is continuous. Fx is continuous for all negative real numbers. Okay? Fx is continuous for all negative real numbers. Then we go for case 2. In case 2, we work at 0. Okay? At x equal to 0, we will work it out. At x equal 0. At a particular point you are working, you take x only. If you are working for representing for many values, you take c. Okay? At x equal 0, we are working. Then what is f of 0? F of 0 is 0 only. Right? F of 0 is 0. Whether we need to work it out left hand and right hand limits? Yes. You need to work it out left hand and right hand limits here. So, limit extends to 0 minus fx. Because the function is splitting at 0, so we have to do left hand and right hand limits. Minus x, so minus 0. 0 you got it. Okay, LHL. And RHL, limit extends to 0 plus fx. So limit extends to 0. The function will be x, because 0 plus, that means you are approaching 0 from right side. That means the value will be more than 0. So x. So the x we have substituted. What we got? 0 this is. Right? Now, LHL equal to RHL. Limit extends to 0 minus fx is equal to, limit extends to 0 plus fx equal to 0, you got it. That means limit extends to 0, fx is equal to f of 0. Therefore, what I can conclude, therefore, fx is continuous. Fx is continuous at x equal to 0. Now finally, case 3. Case 3, right? So we'll take the final case is for all positive reals. Let c greater than 0. Let c greater than 0 be any real number. Be any real number. Then f of c will be what? Plus c. Because for all positive values for all positive values, C greater than 0, right? It is C. So, f of C is C. Then we will find out limiting value, whether we need left hand and right hand limits, not required, because we are working for all positive values. When it is more than 0, the function is not changing anyway. So, limit x tends to C fx, which is equal to limit x tends to C, the function is x here, which is C. Therefore, what I can write now, limit x tends to C, limit x tends to C, fx is equal to f of C. It is true for all C greater than 0. That means what we can conclude now, fx is continuous, fx is continuous for all positive real numbers. Okay, for all positive real numbers. See that in case 1 we proved that the function is continuous for all negative real numbers, and in case 2 the doubting point 0. Why I call the word doubting point? Because there is a chance of discontinuity at 0. Why? Because the function is splitting at 0. That's why I call it is a doubting point. Okay. So, there may be a chance of discontinuity, but here it is continuous, and in case 3 fx is continuous for all positive real numbers. That means what we have proved from case 1, case 2 and case 3, the function is continuous throughout the real number system. The function is continuous throughout the real number system. That means in its domain, the function is continuous in its domain. That means simply we say that the function is continuous. Okay, you are right. By case 1, case 2 and case 3, the function is continuous. Okay, by case 1, case 2, case 3, what we can conclude, the function fx is continuous on R, or otherwise simply we can say simply fx is continuous. There is no point of discontinuity. There is no point of discontinuity in this. So, fx is continuous. So, for more understanding sake, we can work it out some more questions. So, I just take one more question. It is a very important model. Splitting questions are very important. Fx is equal to, okay, so next question, discuss the continuity, discuss the continuity of the function, discuss the continuity of the function fx is equal to x plus 2 if x less than 0, x plus 2 if x less than 0, minus of x plus 2 if x more than 0, x less than 0, x more than 0, right. Okay, see this here, this is a function, observe carefully this function, fx is x plus 2 if x less than 0, minus of x plus 2 if x greater than 0. When you observe it carefully, the function is splitted at 0. The function is splitted at 0, right? Less than 0 one function, more than 0 one function. And one more point you have to observe, at 0 they are not defined. At 0 they are not defined anything. That means what is its domain now? Its domain is R minus singleton 0. R minus singleton 0. From the hypothesis, from hypothesis, that means from the given thing. From the hypothesis, it is clear that fx is defined for r minus singleton 0, okay, because they not mention anything for 0, right. So, domain of fx is r minus singleton 0. Now, how many cases we have to work? Only 2 cases we have to work. One is less than 0 and another case is more than 0. Only 2 cases we have to work it out. Case 1. Case 1. What is it? Here, let c less than 0 be any real number. Okay? C less than 0 be any real number. Then f of c is what? What is f of c? F of c will be c plus 2, right. Then is it necessary of left hand and right hand limits at c now? No, not required. For less than 0, only one function is there. So, that is why limit extends to c, fx is equal to limit extends to c x plus 2. So, you are getting c plus 2, right. So, limiting value is same as, so limit extends to c, fx is equal to f of c. It is true for all c less than 0. That means fx is continuous, for all x less than 0 or for all negative values. Case 2. Now, let c greater than 0. Let c greater than 0 be any real number. Be any real number. Okay. Then f of c, functional value. F of c is what? Minus c plus 2, right, because f of x is minus x plus 2 if x is greater than 0. Now, f of c will be minus c plus 2, and then we will find out limiting value also. Limit extends to c, fx is equal to limit extends to c, the function c is more than 0. So, function is minus x plus 2. So, it will be minus c plus 2 you get, because it's a polynomial, no, linear polynomial. I just right away substitute, that's it. So, limit extends to c, fx is equal to f of c, we got it, right. It is true for all, c greater than 0. From case 1 what we proved, it is continuous for all x less than 0, and from case 2 we proved that fx is continuous, for all x greater than 0. That means what we can conclude now by case 1 and case 2. By case 1 and case 2, what we can conclude is that the function is continuous in throughout its domain, right. It is continuous in its domain. So, we will say that simply the function is continuous. There is no point of discontinuity here. Within the domain only we are working, right. So, we will mention it. By case 1 and case 2, the function is continuous in r minus singleton 0 in its domain. Hence, f is continuous Okay. So, we will end up this session, and still some different types of problems will work in next session. Okay. So, in the third session, we are going to see some more different type of problems in this. Okay. Thank you.